The Stern-Gerlach experiment conducted in 1922 involves shooting individual electrons. It reveals a quantum property that every particle has: the spin. Before quantum mechanics was completely established, particles were thought to always behave as dots moving through space. It turned out that they behave as particles only when they are detected, but behave like waves when they are not. Stern and Gerlach made electrons pass through a special kind of magnetic field. They placed a detection screen after that. The electrons were detected only at two specific places in the detection screen. But these were electrons shot in exactly the same setup, sometimes being detected up, and sometimes being detected down. The magnetic field was passed along the z direction for this setup, so we call this a Stern-Gerlach apparatus on the z direction. We call the particles being detected up as being in the up state, and likewise for the down state. After passing through the magnetic field, the electron behaves as a wave moving in two directions. Then, the wave gets to the detection screen, and the electron is forced to choose one of the two directions. This is called state collapse, and it is fundamentally random, illustrating the probabilistic nature of quantum mechanics. It turns out that we can make this more interesting. We can block the down direction of the electrons passing through the Stern-Gerlach apparatus in the z direction by putting a detection screen only in the place where the down state is. In this way, if there is no electron detected in the down state, we know it is in the up state. We then place a Stern-Gerlach apparatus in the x direction for the electrons coming in the up state, and add a detection screen after that. The last detection screen is now hit in two positions, which we call right and left. We start counting the amount of electrons at each detection site and calculate percentages. The more electrons we shoot, the more stable the percentages of hits of electrons at each detection screen. At the down state, we get 50% of hits. At the right state, we get 25%. And at the left state, we also get 25%. What this tells us is that the electron had two possible states to be measured in, after the first Stern-Gerlach apparatus. And if we block one of those and place another Stern-Gerlach apparatus in the x direction, then we still get two possible states for the electron to be measured in. But now we will make it even more interesting. We will block the left state and only let pass the right state. Then we place another Stern-Gerlach apparatus in the z direction and put a detection screen behind it. Again, we count the electrons hitting each detection site, and we compute probabilities as we shoot more and more electrons. These probabilities can only be calculated with the framework of quantum mechanics, by treating the spin of the electron as a quantum superposition of two states on different stages of the experiment. The important part is that, if we think about this experiment classically, for example, thinking of the detection sites as filters. The first detection screen will be filtering the up and down states and only letting pass the up direction. However, if these were filters, after the third apparatus, we shouldn't be able to see the down state anymore. But we do see it. And this can only be explained by the mathematical framework of quantum mechanics.